Okay, now we start now. We are going to continue that our 8085 instruction set. Now you have to take that another instruction sub. Sub is subtract from accumulator, right? Now you see this one stop subtracts. Okay, you will see. Right? So we are having that instruction subtract. Subtract is subtract with that registers, right? So register means P register, C register, D register, E, H, L, and also we can have a memory, right? So the content is actually we are having now that what about that instruction is here. You see this one, the content of operand are subtracted from the content of accumulator. Subtracted from the content of accumulator. So what you mean by that one as a equal to a minus b. First one. So similarly here a equal to a minus c. So and so on, right? So here last one is a equal to a minus the address of in that content of HL pair address, right? So that is we are having now. So this is we are having now corresponding registers, right? So here now if you are having that value, value a equal to something, right? So a equal to 40 and b equal to 30. So these are all hexadecimal number, right? So if we are having now that you are doing the subtraction, so you will get now in that accumulator is 10, right? So suppose we are having now we are having now 73. Here we are having now that b is 27. So what you will get now that result is here we are getting that this is 7. We are taking one borrow from here. So we are taking one borrow from here is hexadecimal. So we are taking now 16. 16 plus 3 19. So 19 minus 7 12. 12 is C. We are getting now this one 6. 6 minus 2, that is 4. So we are getting now the result is 4C. So here we are getting now that result is 10. Right. So this is subtraction, right? Now if you are having that negative number, right? So if you see this one, we are having now that number is a is 30 and b equal to 40. Now what will be the result, right? So here we are having now that one 30 30 minus 40, right? So generally we are getting now that result is if you are as a number we are getting now the result is 10, right? So otherwise I will tell in simple manner. We'll tell in simple manner means small number we will take and then we will explain that one another cases, right? So here okay. Now you see this one, we are having that number as here we are having that a equal to 2, then b equal to 5, right? So we are getting now the result actually minus 3. So we are subtracting that one, then we are getting now the result is minus 3, right? So minus 3 is a fine negative number. So the negative number is represented in 8085 as 2's complement. 2's complement, right? So how do you get the 2's complement for this 3? Number 3 is we are having 2-digit number, that is 03. So 0 is we are having in the hexadecimal form 4 zeros and followed by we are having 3, that is we are having now 00. 3 is 11, right? Now how do you get the 2's complement is just you have to invert that number. You are inverting that number and then the after inversion we are adding one here, right? So we are getting now that result is here 1 1 1 1 then followed by 1 1 0 1, right? So that is here 1 1 1 is 15, then 1 1 0 1 is actually we are having now D, right? So we are getting now that result is in the form of FT. We are getting now the result is in the form of FT. This FT is nothing but minus 3, the 2's complement of that minus 3. So minus 3 is represented in 2's complement form. We are getting now that one as FT. So if you have that one, then we are getting now the result is FT only. So that FT is negative number. So the last digit is we are having that this is actually we are considering as this number, right? So here we are considering now the total content is going to have that one as FT. So we are getting now the result for these cases. We are getting now the result is FT because of 2's complement of the negative number. This is 2's complement of negative number, right? So next we are having now the next instruction is we are call it as subtract with borrow. Next instruction is subtract with borrow. Borrow is actually we are having now the previous, suppose you see this one here, I told you that one subtract with borrow, right? So that is we are having one number, then we are having 16-bit number. 16-bit number means here we are having first two digit and next two digit we are having now that number, right? So if we are subtracting that one, then we are getting now that suppose this is small number and compare with that one, then we are taking a borrow from here, right? So that is we are taking the borrow from here means then we have to consider the previous digit. We are taking this as 16. If you are taking one borrow, that is 16 because of the hexadecimal number, then we have to add that number, then we are going to subtract. While doing that one, then we are making the borrow, right? So this borrow is going to be considered for next two digits. So this is first two digit, then higher digits, so 16-bit, right? So this is we are having 8-bit, this is the 8-bit, then another 8-bit. At that time, we are getting now the borrow. The borrow is going to be considered while subtracting this number. So that one as we are having now subtract with borrow. So next instruction we'll see. Okay. Now you see this one. Okay. Tell it. Okay. Now subtract with borrow. So we are having that instruction name is subtract with borrow, SPB. SBB is the subtract with borrow, right? So if you are having that previous borrow, that one as we are having now, that's here actually there is no signal for borrow, right? Instead of borrow, you consider now carry. So we are using now the carry is here, right? So that is we consider now as here. As usual, that registers and memory. Registers and memory you have to take now. Next one is subtract with immediate. Subtract with immediate as SUI, right? So SUI is a instruction. We call it as subtract with immediate. Okay. Next instruction is subtract with immediate. Subtract this one is SPB. So SPB is if you are having number that number is 45, then we are having that number is 35. Already we are having that one borrow, right? So that borrow also we have to subtract it. So 45 23, then we are getting now the 5 minus 3 2 and 4 minus 2 2, and then we are having subtracting further one. So we will get now that this is 21, right? So this is previous borrow. Borrow is there, then we are having now that number 21. Subtract with borrow. Right. Next, subtract immediate, SPI. SUI. So SUI is subtract with immediate. Subtract with immediate. SUI 45, right? SUI 45. So that is A minus 45. We are getting now the result in A, right? The result in A. So A minus 45. This is the result, right? Okay. Next one, subtract immediate with borrow, right? That is SBI, State Bank of India. Not State Bank of India. This is subtract with borrow, SBI, right? So SBI, we are having now that one as here you have to subtract that A minus 45. If you are having that borrow is either 0 or 1, so that depends on the borrow, then you have to subtract the borrow also. We are getting now that result. So subtract and with borrow. We are getting now that subtract with borrow is a instruction, right? So where we are having subtract immediate, so immediate means we consider as data, right? Subtract immediate with the data. So whatever that 8-bit data we have to consider, now we have to subtract now. So it's single instruction. So accumulator only we are getting now, right? No other registers is not possible here. Here also we are having that only one instruction. So that one is using that accumulator only. No other register cannot be used. So if you want to have the subtract with the higher number, then you whatever from one register to another register you have to move, and then you have to use, right? Suppose we are having now p register content, you want to subtract with borrow, then how do you do that one? As first you have to move that register content into a, and then we have to call that subtract with borrow immediate 45. So this instruction, and then we have to once again, then you have to move back as b comma a. So p register content is going to move to a, and then we have to subtract immediate with 45, and then the result is going to be move back to b. So that is if p register content is going to have subtract with immediate. So that is the case you have to consider. So you take proper idea, and then you can use proper register. That is very important, right? So as like in compiler edition, how do you allocate registers? So here we are having only the limited register a b accumulator p c d h l, right? Then other stack pointer program counters are special purpose registers. So next we'll consider now the next instruction inr, right? So inr, that is you consider as increment register. inr is increment register. INRS increment register. Now you take the cases. Next instruction INR. INR with all registers, right? So A register increment we can have now, B register, C, D, H, L, and also we can have now memory, right? So that one is here H register, L register we can have now. Here this is memory, right? So memory. So INR memory means INR M is actually what it will do now, HL equal to HL plus 1. This is INR M, right? INR A equal to A equal to A plus 1. So A equal to A plus 1, B equal to P plus 1, then C equal to C plus 1, and so on, right? So this is L equal to L plus 1. So this is the case you have to consider now as INR. Next instruction is INX. INX, right? So INX is register pair. So we have to give that argument is register pair. Argument is register pair, that INX, right? So that the instruction is called INX. So we are having a register. The register is either HL pair. So we can have now INX H, right? So H means actually you have to consider now pair. HL equal to HL plus 1, right? Then we are having now that one as INX B. So we are having PC pair. PC equal to PC plus 1. So already we are having PC pair is something negative, right? Then we can have now INX D. DE pair equal to DE plus 1. So that is we are having now that instructions, right? So you have to consider now. Okay, so you take now as INX, right? INX with the registers. So we are giving that single register, but it will take now the register pair, right? The content of definite register pair. So you have to take this one as register pair color. So you have to consider now this is a register pair. So you have to take it as properly as register pair, right? Sure. You go for the next instruction. Similar way, we are having DCR, decrement register, decrement register with pair, right? TCR, TCX, right? So here as like the INR, here we are having TCR, DCR, then we are having DCR now, right? We are having now DCR, decrement register, right? So decrement register with memory or memory by 1. So we are decrement. TCX is register pair, right? So that is implied. The next one, important instruction. This is very important instruction as decimal adjust accumulator. So very important instructions. So you have to take care about that instruction. This is we are having now decimal adjust accumulator, DAA, right? This as like a DAW, the design and analysis of algorithm as like, right? So we are having now that one as DAW. right? So decimal adjust accumulator, then this is what actually it is doing now. So we are having that number, the result is suppose in hexadecimal. Now this hexadecimal is going to have that one as here we are having the hexadecimal number, right? 0c is the hexadecimal number, then that number is going to be shown as a uh, this one PCD, right? Binary coded decimal. So that one as here we are having 0c, then automatically it will add 6. If you are adding 6, what you are getting now, that one as c is 12, then added with 6 we are getting now 16, then the 18. So 18 is going to represent by 1 2. So 18 is going to represent by 1 2. How do you, that one is in the hexadecimal form 16. So we are having 16 one time and the remainder is 2. So we are getting now the result, right? So if suppose we are having now this digit is having that instead of 0 to 9, if some other digit, then we are adding 6, then we can adjust that one as decimal. This is a decimal number. So 0c is a hexadecimal, the equivalent decimal is 1 2. 0c is a hexadecimal, then this is the equivalent decimal is 1 2. So how do you get that equivalent decimal is just we are adding 6. 06 is added with 0c added with 6, we are getting now that 12, right? If you are having already, if you are having 09, then it won't add 6, no need of adding 6, right? So hexadecimal also 09, then by decimal form also 09. So there is no change is required, right? Whenever we are having this digit is a b c d e f, at that time then you have to add 6 to adjust the that number, right? So this is we are having now hexadecimal, then the binary decimal mean, then we are going to have a decimal as tens digit, right? So instead of the 16s, then we are having now in terms tens. 0c is 12, so we are representing that one as 12, right? So we can call it as decimal adjust accumulator. So if you are having that result is we are having 0c, now we add one more instruction called decimal adjust accumulator. Now the 0c is converted into 12. So whenever you want to display the content in decimal form, then before that we have to call this instruction. So for that purpose we are having decimal adjust. I already told you that one, we are having that auxiliary carry. This auxiliary carry internally is using now, right? So auxiliary carry, what you mean by the auxiliary carry is, if you are having 0A, the auxiliary carry will set. 0B auxiliary carry will set, right? 09 auxiliary carry won't set. So whenever the auxiliary carry is set, now it is adding 6 by decimal adjust accumulator, it will adjust the decimal number. Once again, I'll tell that one. This instruction automatically add 6 if you are having that decimal is in the form of the letters, right? A, B, C, D, right? So that one as here, once again I'll tell that one. If you are having that number 01 to 09, there is no change. This is a hexadecimal number. This hexadecimal number equivalent to decimal is 01 only, 09 only, right? If you are having now hexadecimal number 0A, this is adjusted with added with 6. So you are getting now that one as 10, A equal to 10 in the decimal form, right? So 0A, then we are adding 6. 0A is 10, 10 plus 6, 16. 16 is represented by 0 and 1 carry. So that is we are getting now 6, right? So whenever we are having that letter, then A, B is 11, then the C is 12, right? Then we are having now the D is 13, E equal to 14, and F equal to 15. Then after the 15, right? After that we are having now 16. That is 10 is we are having now, this is 16, so this is not considered now. So that is we are having now, in that case only it will adjust. So that is the decimal adjust accumulator is adding 6 whenever we are having now that particular decimal, right? Similarly here, right? So that is we are having decimal adjust accumulator, right? So that is we consider now another cases. So that is decimal adjust accumulator consider now, right? That is, I told you that one of the auxiliary carry, right? So that is here, this auxiliary carry is used. So this is auxiliary carry, right? If you are having that less than, greater than 9 is the letter, right? So A, B, C, D, E, F, right? So this is greater than 9. A, B, C, D, E, F. For that case, we are adding 6, then we are in section add 6 to adjust that one as lower bit, then we are having now getting now that result is in the form. Right? Okay. Continue now. Right. Next we are having some conditional instruction, jump instruction. We are having that instruction called jump. Right. Here JMP is a jump instruction. Right. So we are having jump to where? Some address. So we are having now the hexadecimal address we have to give, right? So we are having a program. In that program, we want to change the sequence, right? JMB with some address, right? This address may be a previous address, or this may be the next coming address, right? So we are having this jump instruction is skipping that some set of instructions. Then for that case we can use now as, right? So that is we are having now that instruction, it is going to have either this location, right? So this is skipping that instruction, right? Or otherwise the jump instruction go back as a loop, then we can go for, right? So without conditions, right? Unconditional jump. So whenever we are having this jump instruction with the address, the corresponding address, so what it will do now, actually this address is going to be loaded into program counter, right? So program counter is having the current instruction execution, right? Current address of the current instruction execution. Now here we are having the PC is executing the jump instruction. At that time the PC is loaded with this address, then automatically we are skipping that one to the corresponding location. Then program counter start continue that execution here. So this is we are having now as jump instruction, right? Now jump with some conditions, right? So that is for all cases we are having jump on carry. If carry flag is set, then only it will do that operation, right? Otherwise it will skip the operation, right? Jump on carry with some address, right? So if a carry flag is set before previous that instruction, if you suppose we are executing, the carry flag is set. Now it will check the flag register, the flag register content. In that flag register we are having the C pit is contain now 6 means, then only it will effective and it will execute, right? If suppose this carry is 0, just skipping the instruction, right? Instead of this case we are, it will put now no operation, so it will continue the next instruction without skipping, right? So jump on carry, jump on no carry, jump on positive number, jump on minus number, jump on 0, jump on no 0, jump on parity even, jump on parity odd, right? So that is parity even, parity odd is used for communication, serial communication, right? So that is if you are having now the parity check, if the parity is error, then the corresponding data we are receiving that one as error, right? So parity error. So parity even parity, odd parity. If the parity is missing now, then it will give that one. So that is actually we are using now for communication. You don't worry about that one. Just we are having these are all the conditional, right? So conditional. So when the condition is occur now, carry flag is set, right? When condition is 0, reset, then we are having now, right? Then sign flag is 0, that positive. Sign flag 1 is minus. Then we are having 0 flag 1 is that total result is 0. Jump on 0, jump on no 0, right? So jump on 0 is used for the count, right? Counter, the counter is decrementing now until it's reaching 0, then we are having in that loop, right? So counters we are going to have now. If you want to have the 10 times you want to that have the loop, then what we have to do is the count register, C register is going to have a 0 9. Then every time we are having now that instruction called decrement register, every loop we are having decrement register C, then at one time it will reach to 0. C reached to 0, then that reached to 0. Now we are having jump on 0, we are having that instruction, then the loop is going to be discontinued. So for that case we can have now that one, this register, right? So that these are all the conditional flags, right? So we are using the flag and then you can use it. So many instruction is going to use now hereafter. Sure. Next, call, right? So that is in that assembly language program, if you want to have that function call, you have to use that instruction called call. So this is actually instruction called call. Okay, here we are having that instruction as call, right? So call with some location. So the location is now nothing but a subroutine, right? Subroutine is a function, right? So we are writing a program. Now we are having a subroutine. The subroutine is start with one location where we are having now the subroutine instruction assembly language code. The final we are having now return. So the RET, we are going to see that instruction later. So that is we are having return. So the return instruction is here as like that in C language function call, while function call at the end of that function automatically it will return, or otherwise we are using that name is return 0, right? So the return, right? So what actually we are having now in that main program, you are having this function call, then it will execute this a separate code that is called subroutine. Subroutine is the function definition. As like that function definition, here we are having a subroutine for this particular function, right? Now we are calling that function means, then we are having now this is a call, right? Before the call, whatever the context is saving now, then we program counter is loaded with that address. Now it will continue that your control is going to have that one, it will execute the function call. After completing the function call, it will return. So at that time, that what is the next address, right? So suppose here we are having this next address location. Now this next address is in the stack, it will place as like that context switching, it will place in the stack. Then while return, it will take that address from the stack and place into SP, right? So that SP is stack pointer to HL. So that one is stack pointer to PC. So we are having moving that one, then the program counter is continue now, right? So after return, so what the sequence we are having now, that one is we are executing that one, the function call, it will go for the function call and it will execute, and then it will return back to here. It will continue the next statement, and it will continue now after calling the function. So this is the way of we are using the call, right? And also the call with conditions, right? So next one is call with condition. So we are having now, this is call with condition. So call with, this is address, right? So address of subroutine. So that is we are having now. Suppose you are writing that subroutine in 9050 or 8050 8200, right? So your program is 8000. 8000, that from that 8001 to something, right? So we are having now 8000 to 4 or something. Here 8200 we are having the subroutine, right? So here we have to give now 8200. Right? So the instruction is call instruction. The call instruction we are having a code. Then this 8000 code 200. So it will go to here and it will come return back. Then it will come to that location and it will continue now that cases, right? Now that is the call with the condition, right? Next one, a call with the condition. So all conditions as like the previous one, we are having the with the conditions we are calling now. Call conditions, right? That is we can do, right? Next, we are having the return instruction. I told you that one, right? So return instruction is return the subroutine, right? So return what it will do now, from this top of the stack, it will store the return address. While calling the function, it will store the top of the stack, store the content, right? This is it will do the internally, right? This call function internally it will do now. This address is going to be stored. Suppose you assume that one, this is the 8000, this is the 8014. So that the 14 and 80 is placed on stack pointer, right? So the stack pointer is moving to this location, right? The top of the stack we are having this content, right? Then while return back, now this top of the stack is going to be moved to stack pointer, PC program counter. The top of the stack, so this is stack pointer is showing now currently, then it will take that stack pointer content to PC, then automatically your control is returned to this location, right? So that is we are having now, right? Then we are having the, in that return also we are having conditional return with the condition, return with that all condition, right? So carry, no carry, parity, minus, zero, no zero, parity enable, parity even, and parity odd. So that instructions we can have now, right? Now we'll see that instruction PCHL, right? So that was we are having now the content, right? So this is the content of register HL copied into the program counter, right? HL pair, in that HL pair we are having one address. The address is going to back to PCHL, right? So that is the HL content is copied into program counter. So that one is here we are having now. The HL content is going to copied into PC pair, right? So HL register content. If suppose HL register content is we are having now 8200, right? So that is 8200. Now a PC is having something. Now if you are executing this instruction, right, then the HL pair content is going to be copied here 8220. Then automatically the next instruction execution is go to that 8200. Program counter is actually next instruction execution address. Next one is restart. Restart with here where we want to restart and something, right? So restart 0, restart 1 up to 7 is there. Then it will go to that some routine. So the routine is there in that case. Then in what way we have to restart? In what way we have to restart, right? So like we are having 0, 08, 10, 18, then 20, 28, 30. So this is the address where we are having some routine. Then the restart is will go to execute that locations. Restart will go to execute that location, right? So that depends on the restart, then it will do some background operation. You don't worry about that one. Just we consider now, if you are having you are using this restart something, then it will go for execute that corresponding subroutine. Subroutine is actually internal work, right? You don't no need to write anything for that subroutine, right? Restart address. Similarly, we are having now the trap. Trap is actually the trap is also one interrupt instruction. Then we are having restart 5.5, 6.5, 7.5. Then the corresponding address is 24, 2C, 34, 3C. Don't worry about that instruction. Just we are having this is actually we are having that interrupt instructions. Then whenever we are using now that interrupt, we can have. Right. Next instruction is compare instruction. Next instruction is going to have that one as compare instruction. Going to have that instruction is compare, right? So compare instruction, what actually it will do now? That is we have to consider, right? Compare instruction, it actually it will do now compare with all registers, right? P, C, D, H, L and also memory, right? So this is actually what it will do now. It will do the operation of that A minus B, and what is the result? It depends on the result, the flag only will set, right? So it won't change any accumulator content. Just it is subtracting, it is using that temporary register, it will do that operation. This operation is going to affect the flag registers, right? So compare is going to affect the flag register. How it is affecting now? If A less than B, right? So that is here A less than B means here this is 20, this is 30. So it will set now carry block, right? So carry block is setting now. So that is a negative number. So we are getting now that one as carry flag is setting. If you are having that A is less than B, then the carry flag is setting now. A less than B, the carry flag will set now, right? Then A equal to B, then the result is 0, then it is showing that 0 flag is set. 0 flag is set. So 0 flag is set now. So that is we are having now. 0 flag is set. Next one is A greater than B. So both flag won't set, right? So that is reset. 0 as well as carry flag is reset. Then it won't affect any register content. Just it will affect only flag register. So the compare with the content of accumulator, both content are preserved. So the content is A and B, the contents are preserved. It will affect only the flag registers. Right, flag register is here carry flag and 0 flag is affecting now, right? Next one is compare with immediate. Compare with immediate means the comparing the data, right? So that is we are having now CPI. Compare with immediate, then instead of that register and memory, we are having some value. Then that value is going to be compare, then the same effect of that cases. So what is that same effect means? Then we are having that A greater than data and A less than data, A equal to data, A greater than data, corresponding carry 0 and carry 0 is reset. Next we are having now AND with accumulator. AND operation with accumulator is ANA, right? AND operator with immediate. AND operation, right? So the logical AND operation is here. We are having that A register content is something and P register content is something. Then we are having bitwise AND operation, logical AND operation, right? So that is we are having now. Here you see this one A register content is here we are having now 45 and P register content is suppose we are having 25, right? So 45 is represented by 0, 1, 0, 0. Then here 5 is 0, 1, 0, 1. right? Then here to 25 is 0 0 1 0, then here we are having 25, right? Now AND operation is here we are having 0 1 0 1, then here we are having 0 0 0 0, right? So that is we are having 0 5 AND operation. We are getting now that result, right? So that is AND operation with registers and memory, AND operation with immediate data. Now exclusive OR operation, right? So exclusive OR operation is here, the corresponding bit, one bit is 1, another bit is 0, or one bit is 0, one bit first bit is 1, then another bit is 0, then we are getting now that result is 1 1, right? This is exclusive OR operation. Then if both are 0, the result is 0, both are 1, the result is 0, right? So that is exclusive OR. Okay, so that is exclusive OR. So exclusive OR with registers and memory, then exclusive OR with immediate data, exclusive OR with immediate data. So immediate data is we are having exclusive OR operation with 86. Then OR operation, right? OR operation we are doing now. OR operation, all of you know that one. 0 for 0 1 1, then 1 1 1 1, then 1 0 also 1, right? So whenever we are going both are 0, the result is 0. That is OR case, right? This is we are having now OR operation. So OR with the OR with accumulator, OR operation with accumulator with along with register and memory. Here OR operate with original data, direct data. Next one is RLC, rotate accumulator left. Next instruction is rotate accumulator left, RLC. Right, this RLC is doing now, right? So that is we are having now this rotate accumulator, right? So that accumulator content only we are having now. Then see that, right? So accumulator content is, suppose we are having now 1 1 0 0 0 0 1 1 we are having now, right? So you assume that one, this accumulator content is this content, right? 8 bit, right? Now here what actually it will do now, the rotate left is here, right? So this particular bit is going to have that value here, and each bit is moving now the left directions. Each bit is moving now left direction. So this bit is going to come now here 0 1 1 1 0, then 0 1 1 1, right? And also this content, current content also copy in the carry flag also. So the carry flag also is copying the last MSPC bit is copied. So whenever we are having one, that one, right? Whenever you are, so but the rotation is going to have this one, right? So that one is modifying that carry flag also. So that is we are having RLC. Then here we are having T7 to, that is D7. D7, this is D0, last one is T0, right? T7. So that one is going to have now that T7 is placed in the position of T0. T7 is placed in the position of T0. Then everything is moving one bit left. So we are having now this T7 content, right? The modified the bit T7 is affecting the carry flag. That is RLC, right? Then rotate right C. Next one is rotate right, so that is in the right directions, right? So that is instead of that one, then we are having that rotate that one as in this direction, reverse direction, right? So this is in that direction, right? So this is in opposite directions. That is we are having now the rotate right, RRC. This is RLC, right? Next one as RAL, right? So that is next instruction is RAL, rotate right along with the carry, right? So that difference is here the carry is modified, the content is modified with carry, right? The next one is RAL, rotate accumulator left with the carry. Carry is not mentioning now, so you have to be careful with that one, right? So that is we are having now this instruction RAL, right? Not RLC. RLC is without just modifying the carry only. Here we are having now it will shift through the carry flag, right? So this is a carry flag, then this is a 7 register. Now this T7 is going to move to carry, and then the carry is going to move to here, right? So that is we are having now that RAL, rotate accumulator left. So the RAL is including the carry flag also, CY and accumulator RAL, right? Then RAR also including the carry flag. So carry flag is placed in the most given position, right? Right. Next one is complement accumulator. Complement accumulator. Then complement accumulator here, right? So CMA. Just we are having now the complementing that accumulator, right? So CMA is complementing that accumulator. So complement is here. Suppose we are having this value. Currently we are having this one, so it will complement 0 0 1 1, then 1 0 1 0. So that is, it will make that content is complement the accumulator. Next one as CMC, complement only carry flag, right? So carry flag complement is, if carry is already 1, it will convert it into 0. Then if carry is 0, it converted into 1, right? So that is, we are having now complement carry. Next one, set carry. So whatever the carry is currently is carry, it may be either 0 or 1, but it will set that one as 1. 1 means is retained, then 0 means it will convert it into 1. So that is set carry. Then next we are having now no operation instruction. No operation instruction is, it won't do anything, just we are skipping one clock pulse, that's all. Just we are having as a instruction, that the instruction is replaced by no operation. So no operation instruction, it won't do any operation. That is no operation instruction, right? That is idle instructions, no operation instruction, right? Next one is HLT. HLT is called is stop execution. Almost all program we are using that, at the end we are having, right? Next one is DI, right? So that is, we are having now disable interrupt, then enable interrupt, right? So the interrupt, whether interrupt allowed or not, right? So you won't allow, then disable interrupt. If you are allowing that one, enable interrupt, right? So if you are having your program, in that program, while executing that one, if you are allowing that interrupt, then you have to call that instruction called enable interrupt. Then we have to continue now. Then in between, suppose interrupt occur, then it will stop your execution, and it will go to the service for that interrupt routine. Then after completing the service, it will return back to here, right? So here we can, it will allow that interrupt, right? So interrupt here, interrupt 6 7 8, right? So that is, we are having the setup instruction in the architecture. You have seen that one, right? So instruction control, that's interrupt control. The interrupt control, we can have many interrupts, right? Trap is one interrupt, right? Then we are having in the interrupt 6 7 8, then 6.5 7.8, like we are having now that many interrupt. That interrupt is allowed, then the interrupt occur, then it will go for the service routine for that interrupt, and it will complete the service, and then it return back to here, and it will continue, right? So if you are having that, suppose you are having a program, it won't allow that interrupt, then you call, before that you have to call that disable interrupt, then this interrupt won't allow until the completion of your program, right? After completion, then you can make it as enable interrupt, then it will allow that one, right? So that is, we are having now, this is not required, this no use at all. So enable interrupt, disable interrupt, we can have now, right? So already it may be disabled, then whenever we need, we have to use enable. But the trap is, it won't use that one, right? Trap is actually, it will allow always. So the trap is a interrupt, that enable and disable interrupt won't affect the trap interrupt. So except trap, right? So the trap won't disable by any cases. Trap is actually high level priority to the interrupt trap, right? So as like that, you are control alt delete in your computer, control alt delete, if you are giving wherever we are having, now it will go for taskbar, right? So that one as like that, here we have to consider trap is a high level interrupt. This high level interrupt won't affect by that enable interrupt and disable interrupt. So the trap is always open for interrupt. So last two instruction. So we are having that interrupt, I told you on the interrupt 7, right? So that is, we are having now interrupt 7 is higher interrupt 6, interrupt 5, and also we can have now interrupt 7.5, interrupt 6.5, interrupt 5.5, right? So that is, this interrupt is disabled by in mid. So you are having now enable interrupt enabled. this is enabled only, then it will allow that this set of instruction, right? So here we are having now this is interrupt, so interrupt pending. If so, here we are setting now this is one means the corresponding interrupt is waiting, then first interrupt is service, then next interrupt is service, next interrupt. So that is we are having now interrupt is allowed, then higher level priority is 7, next level 6, next level 5, right? The 7.5 is more than that one, right? 7.5 is before that one. So this is highest, next level priority, right? So if you are having that priority is given to that important operation, then you have to connect with the interrupt the corresponding interrupt service, right? So that is we are having now the serial IO, right? Serial IO is used for input output data, right? So serial input data, so we are having now that we are getting from the data from outside world to get your processor as transferring the data as one bit 0 or 1, right? This bit value is going to uh, retain here, then we can take that value from this particular register only, we can take that value to your processor, right? Then interrupt mask we can change using the next instruction called sim, set interrupt mask, right? So that is we are having now set interrupt mask is we can set it now, set right of that interrupt. So interrupt mask, right? So we are here we are having mask interrupt 1, right? So 0 is allowed. If you are having, you are making this as 0, right? This interrupt is allowed. If you are having that 1, the interrupt is disabled, right? So that is here you see this one, we are having, this is actually we are having mask enabled. So this is the overall control for this enabled or disabled. Then if it is enabled by 1, then if you are having these are all the 0, then this is allowed, then it will go for the cases, right? So that is we are having now you see this one, T2 0 is enabled, 0 is enabled, 1 is disabled, 1 is shut down. So that one is the corresponding interrupt we can disable. What interrupt you want to disable, then if you want to have that 5.5 is disabled, then we have to make 001. So that is 7.5, 6.5, 5.5, right? Then that corresponding bit is here MSP is 1, right? MSE. So that mask set enabled. So this is the control of the next coming interrupt, right? Then here we are having now the serial output data. So serial output data, we are sending the data out. Sending the data out means from the processor to external world. Processor to external world we are sending the data. External world we are sending the data as in the form of bitwise 0 or 1, right? Then serial data enabled. So that serial data is you want to cut down the serial data transfer, just we have to give that one STE is going to have 0. So we have to make it as 0, then this is enabled, right? If it is 1, then it will allow that serial data transfer. So that also we can do now. So this is the set of instruction, right? So we are completing that all instruction set, right? Then we can continue another lecture for another title. Okay, thank you. We can stop here.